Okay, so just before I tell you the structure of this talk, let me say a little bit about the kind of thing I'm going to be talking about today. So I will today consider theories which have the following formal structure, theories of consciousness, which have the following formal structure. So first of all, there's a space P, and I usually just call this a space of physical configurations. But think of it like, some sort of mathematical space that tells us something about systems, how they're connected, for example, and the corresponding states. So that's one thing. Then there's another space, and that's a space of states of consciousness, right? So it's, for example, telling me whether I see blue or I see red, and I'll denote that by E. And then that's something we have always when we talk about theories of consciousness. But the constraint for this talk is really that I'm going to be looking at theories which determine the state of consciousness as a function of the physical configuration. So what that means is, so I'm going to be looking at theories. So this is a map or a function. So for every p, little p here, it gives us a little e. And that's just written here again. So for every physical configuration, the theory determines a state of consciousness, which will be denoted by T of P. Okay, so let's look at a few examples of this kind of structure. So typical example for physical configuration would in fact be the brain. So, like for example, as described in the level of neurons, typically, so we'd have the brain with the neurons and all the connection thereof, and then for every neuron we'd have a state. So that's a little p in p. State of consciousness, I mean, that's more difficult to, to nail down, but what you should have in mind is really a situation like this. So for example, imagine you're walking down this beautiful autumn road here, and you have all sorts of impressions and feelings and maybe a model of yourself. And we'll just call every combination of those a state of consciousness, right? If we go to more simpler cases, we could maybe just focus on color or just on auditory signals. Yeah, different experiences, different conscious experiences would be different states of consciousness. And what the theory of T then, examples of the theory T are most notably, for example, integrated information theory, right? So where you'd have to know a little bit about how the system decomposes. And then you can apply this very complicated algorithm, which in the end is just a map T. And then that would give you some mathematical structure that makes up this space E. And that mathematical structure is then claimed to be identical to a conscious experience. So for example, what you see here is a picture from this IIT 3.0 paper. And this illustrates one particular mathematical structure, which is called maximally irreducible conceptual structure, tongue breaker, at least in the morning. Some people also call it Q-shape. So that's just basically a large collections of probability distributions, and they're claimed to be identical to a state of experience. So at this point of the talk, it doesn't matter how exactly this identity is being established or what operational meaning it has. What matters really is just that you have this space. But there's basically any other theory among the theories that are typically being discussed in science has the structure as well. So for example, in global neural workspace, well, the space E isn't a mathematical space, which is complicated in the case of IIT, but it's just a simple space where you have for every stimulus that you present to a subject, you have a 0 for no conscious perception and a 1 for conscious perception. Payment the brain proposals, similarly, what they do is they give some sort of definition in terms of fame of how the stimulus or of what constitutes a stimulus being conscious. Higher order thought theories, just to give another example, I mean, I could go on. So again, you have a certain definition which tells you what has to happen in the physical configuration for something to be perceived consciously. And in this case, it's really just that there's, very roughly speaking, I'm sure that's not a very nice way of saying it, but there needs to be a representation of a representation or a thought about a thought. Okay, so the message is that actually almost all of the theories we consider in the science, on the scientific part of it, exhibit this formal structure. So why is this? Well, that's because, so here it is again, you see this was our physical configuration, state of consciousness, and the map. The map is indicated by a little arrow here. Well, the reason we see this structure so much is because you can actually show that physicalism implies that theories of consciousness have to have this formal structure. And in this case, he would really describe, so physicalism very roughly, it says that consciousness supervenes on the physical. So one way of saying that, so maybe let's just say, so the necessary requirement for physicalism is that every minimal physical duplicate of the actual world is a duplicate simpliciter. So that roughly says that whenever the physical is the same, the conscious is the same, and then the T would really just describe the supervenience relation, the particular way consciousness actually supervenes in our world. And so that implies the structure. So every physicalist theory of consciousness has this formal structure. And similarly, so physicalism implies the causal closure, the closure of the physical. And similarly, the closure of the physical would then imply that this structure has to hold for a theory of consciousness. So that's why it's basically a very general structure, but of course, I mean, there's other metaphysical ideas which are not physicalist and they would not have this structure. Okay, and I just want to emphasize one thing which is really important. So otherwise the whole talk is going to be, there's a chance of misinterpretation. And that is that this distinction between states of consciousness and physical states, that is epistemic. So it concerns ways of knowing or ways of gathering information. It is not something metaphysical itself. So that what do I mean by that? Well, basically what I mean is just this. So the starting point of the scientific study of consciousness is that we have two different ways of, let's say, gathering information or gathering data, right? There's something we typically call the first person perspective. There's something we call the third person perspective or the objective scientific perspective. And these are just names, and these words are not supposed to be taken literally, but we have these two different ways, and that's what sort of defines what we even have to do in the scientific study of consciousness. We have to develop metaphysical theories and then scientific theories, and they have to describe the relation of these two different means of gathering information, which give two different states, in the correct way. And so these states in here are really just, like have this epistemic flavor. And I'm saying this because people sometimes think that this sort of language implies dualism. That's not at all the case. So in dualism, you would also have these two spaces of states. You would have them in every theory, but of course the T might be different, but it's not the case that just because of using them, you're obliged to dualism. Yeah, okay, so that's what I wanted to say. And there are some dualist proposals, for example, Chalmers' property dualism, which would also have this sort of structure where T would then be sort of a law of nature and not something that is, like not a supervenience relation of the more physicalist kind. Okay, so much for this. So that was the setup. I'm going to talk about these theories. So what's the structure of the talk? So there's two parts. In the first part, I will actually show that there's a deep problem in contemporary experimental tests of these kind of theories. And that is work which I'm going to present, I did together with Eric Howell in our paper Falsification and Consciousness, which is on arXiv. And then in the second part, I will actually talk about how we we have many models and a lot of wonderful ideas about how consciousness and the physical could relate, but we're kind of ignoring sort of what makes consciousness a problem in the first place. We're ignoring the epistemic context of consciousness. And I'll say more about what this actually means, what I just said when I come to this. And this is in my paper, Mathematical Consciousness, Models of Consciousness, which appeared in Entropy this year. Okay, so in order to, let's just look at, what do we do with these kind of theories, which I've just introduced? Well, we test them. And in order to describe formally what it means to test a theory like this, we need to introduce a new quantity, an additional quantity, and that's curly O. And curly O is a set, and it contains all data sets that can occur in an experiment under consideration. So it's a set of data sets or a class of sets, if you like, right? So here's a picture which illustrates this. So let's assume we're testing IIT, and let's assume we're using fMRI or something. So we'd have the patient here. The patient would be in the fMRI device. He would be another scientist, programming the device to measure the internal state of the brain, for example, to some degree. And at the same time, we'd have a scientist which is collecting reports. I mean, this is a very simple example where the reports are actually like verbal reports. So, for example, the person here could maybe see a screen and would report, I'm seeing green or red, or the person would report something about him or her being, tired or dizzy or something. and we collect the report, and we'll collect the data about internal measurement, and that is one data set together. And all which could occur in an experiment will just be denoted by curly O. Okay, there's two parts which every single data set has. And we also need to distinguish these. So on the one hand, every data set that we collect in an experiment has a prediction content, or we call this prediction data. And so that's actually used for then plugging it into the theory we just had. So that's physical data. It's on the left-hand side of that arrow. And this prediction data we denote as OI, where I just represents internal. And here's just a picture I took from, the source got lost. Sorry, maybe it appears in a minute. But that's a picture I took from a 2014 publication from Nature by Patricia Churchland and others. That just illustrates the kind of possibility that exists in neuroscience for measuring brain states. So what you see here is sort of, here you see depicted the different concepts. So basically you see the size, and that's a logarithmic scale, the spatial size, if you like, and the corresponding things that sit on that side. And what you see here is the temporal resolution that is possible. So for example, here's an fMRI image. So that just describes the area we could actually get access to using fMRI scans. But of course, here's EEG and MEG, single unit recording. That's of course nothing we really do with in the scientific study of consciousness. I mean, there's light microscopy. There's actually many different things we can do to sort of really get down from a very coarse-grained level, maybe here on the layer of neurons, to really down to the level of synapses. And what's not represented, of course, in that picture is that there's different, like how much information we can actually get. Is it just of a small part of the brain, or is it really of the whole brain? And of course, what we want in the scientific side of consciousness, we want to get information about regions of, or larger chunks of the brain, and that's the limitation, at least when you go to this end here. Usually you just have a few neurons. But what this plot is basically saying, well, there's a lot of ways to get information of the brain, and that whenever you do that in an experiment, that constitutes the prediction data in every single data set. And similarly, there's another piece, and that's the inference data. So if we look back at the picture I just used to introduce the data. So the prediction data would really be what the person here is collecting using the scanner, and the inference data would be basically what we use to then infer the state of consciousness. So here's a little R for indicating that that's typically a report. By report, I mean something very general. It could be a verbal report, it could be a behavioral report, it could even be a no report paradigm. But some piece of data we use to infer the state of consciousness. And here, for example, the patient is saying, I see blue. Okay, so if we represent that formally, we have the following situation. So we have our physical configurations, we have our states of consciousness, and now we have these data sets. And there's three formal quantities which matter in order to describe an experiment. And the point is, we only need to know that they exist. We don't need to know what they actually are in order to prove our result. So first of all, there's something we call a correspondence, and that takes every single physical configuration, and it tells us what are the sort of data we could see in the experiment. And, it just gives us a set of data sets. That's not all of all, but a subset thereof, and it tells us that physical system is in your scanner. Basically, that's the sort of data you would get. And then off of that data, there's two things an experiment would do. So first of all, the experimenter would use the theory T that's supposed to be tested to make a prediction about the state of consciousness. And the experimenter would then infer the state of consciousness from the report data. So if we look at that in a little bit more detail, so that's the same picture as here, just that I basically blew up the symbols. So here we have a little p, that's an element of big P, so that's a single physical configuration. And so what that says is, well, there's some function which we just call ops, and that gives us a bunch of data sets, and that's just one of these data sets that could occur in the experiment if we had, say, my brain or me as a subject in the experiment as compared to someone else. And so basically, what we then also said is, and then there's these two different parts of the data set. Typically, they would overlap to some extent, but I just do the non-overlapping, and we use the internal measurements to make a prediction about the state of consciousness, and you use the report whatever the data is that is being collected to infer the state of consciousness. So these are these three functions. And here's the picture again. And so basically now it's very simple to say what's a falsification? Well, if at some particular data sets in the set of all possible data sets, we have the inf map and the pred map not going to the same, well, then there's a falsification. And I wrote it down like this. So basically this means, so we take inf, so we can choose one of them as a function. So we chose inf as a function. So inf gives us an experience we actually got from the report. And pred in fact gives us an experience we got from using the theory in the prediction. And this is in fact a whole set, because in general, you might not always have enough data to actually predict a single state of consciousness with a theory. So as in the other colored example I just had, usually you just get some rough data about the brain and you might end up saying, well, several states of consciousness might correspond to, might be possible given that physical states. And if these two things don't align, well, then there's a falsification. So what does a falsification mean? Well, it means two things. So first of all, it could be the case that the theory is wrong. So in other words, the prediction just goes to the wrong experience, and the one the subject is having is in fact the one we inferred. But alternatively, it could also be the case that the inference is wrong. And maybe the prediction is right and we just misinterpreted the report of the subject. And so a single falsification might not be so bad. So maybe we might be willing to grant that the inference was not correct. But what we then show in this publication is that two assumptions, which I'll introduce on the next slide, they have a rather strong implication. So the assumptions being this one and this one, we'll talk about that in a minute. And they imply that either every single inference operation is wrong. So for all data sets, you do the wrong inference, or the second case here obtains, namely the theory is wrong. So the theorem really tells you that this situation, so basically the theorem tells you what's written here. There's a falsification for every report that you think can be trusted. Okay, so, and the assumptions here are that the theory is minimally informative and that the inference and prediction data are independent. And let me just introduce these assumptions. And what I'll do in this talk now, in order to not to lose too much time, I will not introduce the formal versions of these assumptions, but I will tell you what they mean, what the gist of them is. So the first assumption we need is that a theory is minimally informative. So that basically says that for every prediction, there is at least one data set which gives another prediction, a non-overlapping prediction, if you like, in the terms of the picture we just had. And that's an assumption which is basically always true. Like that's why we also call it minimally informative. If you don't have that assumption, your theory is very limited or your theory is very early in its development. And the assumption that really does the bulk of the work is really the following. So we say that inference and prediction data are independent if it is possible to vary the prediction data in the class of physical systems that could in principle be realized in your experiment. So that's the set P, while the inference data remains constant. So let me illustrate that in a picture. So here's again this definition if you want to read up what I just said and just illustrate it. So basically inference and prediction data are independent if we find a variation. And the variation here is really indicated by these arrows. So we have our original physical configuration, so the system in a particular state. And now we change that configuration to some other physical system. And it doesn't matter which one it is. It really matters that the system is within the class P, and those are systems that could, in principle, maybe not in practice, but in principle have been realized in your experiment. And the condition is that we keep the inference data constant so that the report basically doesn't change, but we change the prediction data, so the internals of the system somehow, and we change them as indicated here in such a way that, and so that's actually then already part of the proof, and there's some work that minimal informativeness does, and I invite you to look at the paper if you want to have more details. But what you basically see is that what ends up happening in the end, if you put all the definitions together, is that these changes are such that the prediction really here changes to such an extent that there's no overlap in these gray areas. So the gray circles describe basically all possible states of consciousness that are compatible with a particular structure about the internal state of the system. And you can see already from this plot, which is basically indicates the proof also a little bit, you can already see that, you know, even if this inferred state of consciousness would align with one of them, it couldn't align with the other because they're non-overlapping. And that's the gist of the result. Yeah, so maybe just to say it again. So what we prove is that if the theory is minimally informative and if inference and prediction data are independent, well, then there's something we call universal substitution. And that then implies that, that you really have a problem. Either every single inference operation is wrong, and usually you wouldn't want to grant that because then you just can stop doing the experiment, or the theory is already falsified. Okay, so what does this result mean? Well, first of all, let me point out, so why is this assumption that inference and prediction data are independent widespread, or why do we even do that? And well, the reason is that in contemporary experiments, or you could also say contemporary theories, do not care about, they don't model why or how a system comes to report about its conscious experience. In the best of cases, they have, you know, a general thought in the background, or a general idea about how, you know, like this could be the case. For example, in global neural workspace theory, you could say, well, if the stimulus signal is in the workspace, well, then it's available to report, so the system reports. But the problem is that as long as we work on this general level of analysis, or don't even care about it at all, well, we can also always find, we can tweak the system. For example, by, you know, imagining some sort of implant, we can tweak the system such that it actually gives the wrong report, gives the same report, but has a different state of consciousness. And that's the idea behind inference and prediction data being independent, and why we basically use it so much. So in a certain sense, you could say it like this. Well, we make comparably, like you could say, a naive epistemic assumption about the content of report. So we're very careful, you know, in thinking about what we actually infer from the report, you know, and like in experiments, you really have to be very, like, there's nice methods to make sure that you actually, you know, like to actually justify your inference. But what we ignore is how this inference actually relates to the theory we're testing. And I have a little star here because, so this is not true for all theories. There are some theories which avoid inference and prediction data being independent. And these are theories where the state of consciousness and the report are, sorry, the internal data and the report data are strictly dependent. And I won't talk about this in the talk here due to time reasons. If you want to have a look, it's a section 4 in our paper and it's not so long, or ask me during the discussion session. But that applies to theory where, which somehow equate access to report. That's maybe access consciousness is a bit misleading. It's not, so I don't mean precisely what Ned Block means when he uses this term. But if there are theories which equate the access to report with what then is conscious, the system is conscious of, well, this theory exhibits strict dependency, and that is also leads to problem of a different kind. So that's just saying, usually we have this situation. Sometimes we have the opposite. Both are problematic. There might be a space in between where we can go in experiments if we study, that's what's coming up, if we study the connection between what the theory tells the system is conscious of and what the system reports in more detail. Okay, so what does the theorem mean? Well, as already said, the standard paradigm of testing falsifying a theory that is in use today exhibits a problem. And a way to actually say that very clearly is as follows. So if you do an experiment, you test the theory of consciousness and you do not arrive as a falsification. So for the sake of this discussion, we can say you corroborate the theory. I hope that's the right word. So you confirm the theory. Well, then what this result shows that is, if you have not taken into account how the report actually originates or corresponds to what the theory says the system is conscious of, well, then there will be another system which you didn't test in your experiment, but you could have tested in principle, and that system would have given you a falsification. So in the end, in a sense, what this says is that confirmations of theories in experiments don't matter, because every confirmation comes with another experiment that you didn't do, but that would have been possible and that would have falsified the theory. And of course, that's a problem if you put a lot of money into scanners and experiments. And another thing, another implication, another point is so like basically the unfolding argument, which you might have heard about, which was very famous in the beginning or the end of last year, maybe beginning of this year. That's actually a special case of a problem we pointed out. So that's a special case where you apply to IT, and then in addition, the paper, sorry, maybe I should say that, so the logical structure of the paper as it was originally presented is not sound. There's a logical gap, and you can only bridge that gap, or one way to bridge the gap, the only one I know of, is by making this assumption of independence. You could also say differently, the author implicitly assume without being aware of it and without writing it, that independence holds. And so if you take that into account, the unfolding argument is really a special case of our results. And what our results show then is that this problem is not at all a problem that only applies to IT or recurrent processing theory. It actually holds because of issues with the underlying paradigm of testing theories, and that applies basically to all theories of the formal structure I've indicated in the beginning, unless you go to strict dependence. And I should say, so to all contemporary theories, the goal, of course, is then to actually build theories or conceive of experiment, and it has to go hand in hand, where we model how the system comes to report about its conscious experience. And as soon as you do that, you actually go to a realm which we have called, I think we call it lean dependency. I'm not sure at present, but basically you can go to a space where you don't have independence and you don't have strict dependence, but you have there may be sort of a way in between which works then. So that's what's written here. So the upshot is that when building models of consciousness of the type considered here, we have to consider the connection between conscious experience, according to the theory, and the report explicitly. We have to model that, and only if we do that can we actually avoid this problem, and then sort of make sure that sort of the methodology used in the experiment doesn't defeat itself. Okay, so that was the first part of my talk. I'm very happy to take questions. I hope I made I hope I made it somehow clear what we do and what it means. And please don't hesitate to ask any question in case there is anything you didn't understand or I didn't represent correctly. Okay. But now I want to come to the second part of the talk, and that's actually more towards theory building in light of consciousness epistemic constraints. Okay, so epistemic constraints, what's that supposed to mean? Well, let's start like this. So conscious experience has some certain, you could say, features, but they constrain our access or knowledge, of consciousness, and therefore they're epistemic features. So epistemic always means relating to the knowledge of, or roughly, or the information we have about. So what is crucial about consciousness from a scientific perspective is that it exhibits these kind of things. So for example, also from a philosophical perspective, I should say, but in particular, my claim is from a scientific perspective. So it exhibits a certain number of epistemic features, and here are just some. So, and I'm just going to read them out. So they're in fact words, but that's not supposed to mean that they're well defined. So I would say that every single one of them I have put here, and there's in fact others, they actually correspond to research programs or debate in the philosophy of mind, where the people are trying to understand what does it mean for the metaphysics of consciousness, what does it mean for, kind of the thing we're interested in, what does it imply for sort of, like knowledge about consciousness, and eventually also what does it imply for any sort of scientific study of consciousness. So that's something that's, at least to the best of my knowledge, is just beginning to emerge a little bit more. Or maybe to put differently, it's something that's in the background of many of the claims we have seen over the past years. Explanatory gap, we'll come to that. Our problem maybe, even though it's not so much phrased in terms of these epistemic features, it's certainly something that happens in the background. Okay, so here are the epistemic features. Consciousness is intrinsic, consciousness is subjective, consciousness is private, consciousness is transparent, consciousness is qualitative. So that just means that basically, the what is it like to be nature of consciousness. It's ineffable, it's unidentifiable in parts, and crucially, it's unavailable in parts to cognitive, linguistic, and verbal processing. And my claim is not at all that all of these are well defined. Some of them are. My claim is also not that all of these actually apply. What I'm saying is just that these are things that consciousness seems to have, and we have to take into account what they imply for the scientific study of consciousness. And the ones which I really want to focus in on in what follows, and the ones which are also in a sense most general and also most important, are the last two. So consciousness is unidentifiable, and I'll have an example where I explain what that means in a minute. And crucially, that's really the one to keep in mind. So some parts of conscious experience are unavailable to cognitive, linguistic, or verbal processing. Okay, and so we'll go to an example in a minute to illustrate what I mean by that, what people mean by that. And the message I'd like to get across is that these features of conscious experience, they induce epistemic constraints, which we have to take into account when we do experience or we think about theories. They limit the access we have to states of consciousness. And that is, in the end, if you want to put it formally, to elements of E. Okay, example. So this is something I made yesterday, and depending on the brightness of your screen, on the background condition of the lightning, wherever you're sitting right now, and probably also whether you have night mode activated or some sort of eye saver in your screen, you might see two shades of red here or just one. So I see two shades of red. Here's the dividing line. So if I go a bit back, I see there's one shade of red on the left and one shade of red on the right. And the point is, so I can distinguish these if they're presented to me. But the question is, which one of the two is this one? And I don't know if that makes sense now, but like, yeah, maybe it takes too much time to actually vote. But if you think about, try to think for yourself, which shade of red of the two I've just presented to you, supposing you could see them. So I've just made that example. I didn't, so I wasn't able, when I made this talk yesterday, to find the actual, the particular shades of red that have been used in experiments where this phenomenon is confirmed. So I just picked some which were very close. Yeah, but which one is this? So I think there's something in the chat. So let me just see if I can find the chat. Here is it. Yes, some person says it's, so that's Hero, and he says it's the right, it's actually a left one. Okay, let's try again. So here's again, so you can see the two different shades of red. If everything happens to work out with the lightning, which one is this? Hero, you want to guess again in the chat? Yes, that's correct. It's again the left one. Yeah. So what this example shows is that while there's certain things you can discriminate in conscious experience, you cannot actually identify it when you see it again. And that's just a limit on what we can know about consciousness. So basically, if I go into an experiment and you show me pictures like that, I will make mistakes because basically I can experience more than I can sort of cognitively process, right? So that talks about the unidentifiability of some parts or aspects of consciousness. It's tough, yes. And another example is actually this one. So this is vertigo. So that's a medical condition, which if you don't know the word, I didn't know it in English before I learned about this. So that's just, you know, very roughly the idea you're spinning, yeah, but it's a medical condition and a very severe medical condition, in fact. And the point is that if people, and I chose this picture because it makes you very dizzy, so you get some sort of impression of what it would be like. And if people, and that medical condition can derive from conditions in your vestibular system, so in the system which contains your inner ear and also the vestibular canals you're using to balance and to control your posture and control your eye reflexes. And if people have this medical condition, it's very important to find out in which direction they think they're spinning, because that points to whether the problem is in one or the other of the vestibular systems. And that's something very hard, and people are actually in many cases not able to tell you. They're not able to identify or process in which direction they're actually spinning. And even worse, in some cases, people have problems in the vestibular systems, so they have these medical conditions, but they feel in their subjective experience that they're not okay, but still they're not able to identify that it's actually a spinning motion. Like before you actually do experience with them, you use some sort of other clues in order to find out that it's actually vertigo and which direction the vertigo is. And so that example is just like one of many examples you could give where we actually have, so we have a conscious experience and we have actually difficulties of processing it cognitively. So it's inaccessible or unavailable to cognitive processing, to verbal processing, and in the end, to report. Okay. So this was just to motivate the last two of these epistemic features of consciousness. And again, there's like a huge amount of work and many important insights about what the others of them would actually mean, how you would define them. For example, concerning subjectivity, there's actually research going on by Martin Rieder-Nümelin, to give an example, where people try to say, okay, what is the subjectivity of consciousness actually in conceptual terms? How do we have to define it? Or Uriah Kriegel, if I pronounce that name correctly, also, like, there's a sort of a contemporary debate going on about this. Okay, so let's get back to the formal side of things. Okay, so we've talked about the unavailability of parts of conscious experience, or in other words, of states of consciousness for cognitive, linguistic, or verbal processing. So how can we capture that formally? Well, let's take two subjects. So this is subject one, so maybe that could be Hiro and that could be me. And so we've talked about states of consciousness. So each and every one of these subjects has a certain number of states of consciousness that ideally we want to understand, investigate in an experiment, and then maybe describe theoretically. And what we would like to do, and what we often assume, is that we can identify these states, at least if we restrict to a certain class, for example, color experiences. So we would like to identify the space of consciousness, the space of states of consciousness of Hiro with the one of me. And so what an identification is just a function. In this case, it would be a bijective function, if we're really able to identify everything. And it just maps a state of Hiro to a state of myself, which could be A2. And if whichever one it hits, that's then claimed to be identical with the one we have on the left side. And now let's take into account that subject S1 cannot distinguish certain states of consciousness, as for example in these simple examples I showed, but in fact I would claim that's something much more broadly applicable. And in order to model that, for the purpose of this talk, we will just assume that if Hiro cannot distinguish state of consciousness E1 and E1 prime, we'll just put them into equivalence relation. And we'll define that equivalence relation, was denoted by this tilde here. And that's a simplification for this talk. So I tried to put it very simply. If you want to have a fuller picture, which actually starts a little bit differently with the mathematical structure of these spaces, and then uses that in fact to derive sort of empirical well-definedness, you in fact do get an equivalence relation, but not along these terms. So I'm saying this because in the end, it's not very plausible that if I can't distinguish E and E1 prime and E1 prime and E1 prime prime, that I can also not distinguish E1 prime and E1 prime prime. So it's not transitive in the end. So that's why I'm saying this. So I chose this route of getting to the formal structure because that's very simple and I hope intuitive as compared to the details here, which are more grounded and more well-defined, but also more difficult to explain in a talk. Okay, but let's ignore that. So let's just assume whenever things are not distinguishable, we'll just establish them as part of a root equivalence relation. So what that means is that we can't, and then equivalence relations give equivalence classes. So an equivalence class basically consists of all states of consciousness now, which I cannot distinguish among each other. And so what this basically means is that sort of instead of being able to actually identify individual states of consciousness, we can only identify equivalence classes. So we'll have some map. Again, which map we choose doesn't matter for the following formal analysis. But we'll take one equivalence class, for example, the shades of red, Hiro can distinguish, and the only thing we can do, we can identify that with an equivalence class that describes the shades of red I can distinguish. And if we were actually to try to map individual states, that's meaningless because we can't distinguish them. So we're doing something wrong. So this is the so-called quotient space. Okay, so the message of this slide is that the unavailability or the unidentifiability leads to impossibility of distinguish, and that in fact makes the map we can use for identification worse. This map has more information than the map we're using down here. Okay, let me just give an example for where this works out, or which connects to contemporary debate. So let's denote these equivalence classes by E tilde. So if I take a state of consciousness, this is now a set and it contains all sets that I can't distinguish from that state. So that's the equivalence class of E. And we can now look at spectrum inversion. So I suppose most of you have heard about this. So that's the idea. Well, while I'm seeing a red strawberry right now, there could be something. Sorry, something could happen to, I don't know, the configuration of my brain or maybe the laws of nature, and that then would imply that I see a green strawberry, but I don't actually, so I can't express the difference in any sort of report or behavior. So what's that then formally? Well, spectrum inversion is just a function which maps the state of consciousness of the first subject, for example, to the states of consciousness of the first subject. So it's something, you can see it in this picture here. I took this from SCP and this from Wikipedia. So you can see in this picture. So that's basically, that would be the state space in a very simplified example of states of consciousness. And I would then map this to this, where the green one would be mapped to the red one. And the key point about spectral inversion is that it keeps all the relevant or maybe all the behavioral responses invariant. So what that means is then that I cannot distinguish E1 was hero, whether hero is actually perceiving red or green. That's something I cannot distinguish from reports or by his behavior, and that's something he himself cannot actually express in this kind of thought experiment. And what that implies then is that this equivalence class here, so maybe let's put it like this. This means that I can only identify meaningfully the set of these two states of consciousness with some of my states. And if I were to identify them individually, I'd do something that wouldn't be empirically well defined. And these states in this example would actually be part of this equivalence class of E1. The equivalence class could in fact have many more states. Okay, so the message here is that spectrum inversion is something that's defined for an individual subject, but it would have implications for the identification. Okay, and in fact, so a word I use to describe this is non-collatable. So I would say a state of consciousness E is non-collatable if and only if the equivalence class of E, we've just discussed, contains more than just the state itself, right? And this definition it's a definition that I can apply to an individual subject, and that's nice in what follows, but it actually contains information or is defined in terms of comparison with other subjects. And that's also why I chose the word collatable. That's a bad translation of a nice German word, which is called abgleichbar. So that just literally means that I cannot identify I cannot identify experience A of the subject I'm considering with a unique experience of other subjects. Okay, and so why would non-collatability, that is what we've just discussed, be a problem? Well, the essential point is that the non-collatable experiences, they can't be referenced intersubjectively, at least in a well-defined way. So if I don't know whether when Hiro says green, whether he actually means green or red, whenever I pretend that I can actually intersubjectively reference his experience of green, I'm doing a mistake, because there's no way, according to this example, that I can actually say something and make sure that this actually picks out the green experience as compared to the red experience, which, if spectrum inversion is a thing, would also be applicable. So that is the key point. I hope I explained this sufficiently. And I'll have an example just a few points down. But science, on the other hand, is irreducibly intersubjective. So if you drop intersubjectivity, you can do very nice philosophy, but science is intersubjective, and that means that non-collatability, in light of this fact, actually induces obstacles. And let's just look at an example to make sure that this is sort of a good way of explaining this. Well, if you look at the neural correlates of consciousness, well, what we want to do essentially, and maybe even today, is we want neural correlates of consciousness of individual experience, not just, of collections of these. So for example, we want to know if sort of E and E prime, and that being two different states of consciousness, what the corresponding neural correlate of consciousness is, roughly the pre-image of the map T I had in the beginning. And we want to use that in order to actually study what the correct theory of consciousness is. But if E and E prime cannot actually be distinguished by a subject be put into the scanner in the experiment, well, whatever we measure, we can't know whether that's something that belongs to the neural correlate of consciousness, so the NCC of E or the NCC of E prime. But E and E prime are different experiences, and therefore, in general, at least, or for general theories, their NCCs would be different. And the same applies for testing theories predictions. And so what this example really shows, it highlights this point here, is that sort of if the subject cannot distinguish these things, right? Or put differently, if states of consciousness are non-collatable, if I don't know how I can sort of identify these states over several experiencing subjects, well, then that restricts the possibility to actually use that very state in experiments. And something I won't go into now due to time constraints, but you can actually think about this in more detail. And you can see that if we ignore this fact, for example, if we use, let's say, the stimulus as a reference and pretend that picks out a unique state of consciousness in the case of color, we're actually doing something wrong. So the conclusions we then get out might, for example, point to the wrong region of the brain as being an NCC. Okay, and just real quick, so I really want to focus on this. This is a big part, but we'll come to mathematics in just a little bit. Not much longer to go. And I just wanted to point out that, so one thing we really talk about is the hard problem. And there's various different versions of formulating the hard problem. And one other thing we often talk about is the explanatory gap. So that's really important for many people. So the idea being that consciousness cannot be deduced from physical laws or facts. And what I emphasize, and there's also a nice paper about this by Eleanor Taylor, is that the usual justification, so justification of the explanatory gap are either intuitive in the case of Levine's original paper, so then it would say they're intuition pumps and not to be trusted. I see it a bit differently, but still they're intuitive. Or if they try to somehow actually give an argument which is not an intuition but something valid, they usually refer to the deductive nomological model of explanation in science, where really explanation is logical deduction. And that's really expressed in the statement here, sort of rough statement about what the explanatory means to many people in these cases, is that consciousness cannot be deduced from physical facts or physical laws. But the fact is, in science, there's many other models of explanation. Or in fact, to put it differently, philosophers of science study what scientists take explanation to be, and they come to the conclusion that the deductive nomological model doesn't actually do such a good job of capturing what we actually mean by explanation. And there's many other models, some of which I've written down here, and there's more which give different accounts of what scientists actually mean when they talk about explanation. And the crucial point for me is we don't know which one of these notions of explanations is the right one we will eventually apply to consciousness. Consciousness studies is something very early in a certain sense if you compare it to other disciplines, which are hundreds of years old in some cases, or at least tens of several decades old. But the point is that all of these models that have been identified by philosopher, they actually assume that the explanandum statement, so the statement that describes the phenomenon that's supposed to be explained, is intersubjectively well defined. While non-collateability, as I've tried to argue on the previous slide, is actually implies that these states of consciousness, which are non-collatable, are not intersubjectively well defined. They cannot be referenced intersubjectively. And therefore, sort of non-collatable states of consciousness actually exhibit a genuine explanatory gap, and not one that is only exists relative to this simplified conception of what an explanation is. So that's just this slide. That's again to motivate that non-collatable states of consciousness are the ones we should actually be looking at. And if we do that, we can actually see clearly where the contemporary scientific methodology actually runs into a problem. Okay, what's the upshot of the previous slides? And I should say, all of this is expounded in much more detail in this mathematical models of consciousness paper of mine. Okay, what's the upshot so far of the second part of the talk? Well, my claim is that what follows from this is that the contemporary use of the space of states of consciousness actually ignores epistemic constraints that generate the problem of consciousness in the first place. We ignore the fact that, we can't actually, in a theory or in an experiment, in case the theory is supposed to be empirically well defined, we can't actually, write down a symbol E for every state of consciousness. We can only do this for certain paradigmatic cases or in certain extremely idealized situations. And if you put it formally, what this means is the contemporary scientific study of consciousness is in fact limited to the investigation of this combination of states. So we can investigate how physical states relate to states of consciousness, but on the left side, we can only consider equivalence classes of states of consciousness. So the equivalence classes, to yet put it in another intuitive way, basically comprises the minimal unit that can be differentiated by the subject in the light of the unavailability and unidentifiability, and maybe some of the other epistemic features of conscious experience. And the contemporary scientific study of consciousness is limited to this combination. We cannot use the contemporary scientific methodology in order to actually address individual members of these classes E. So we cannot use it to address individual states of consciousness that cannot be collated, where I wouldn't know if I address this state, whether that's the same state in another subject, due to science being inherently intersubjective. Okay, so what should we do about this? Do we have to just accept that there is in fact an unbridgeable explanatory gap? Well, an explanatory gap just says there's a problem between the contemporary scientific notion of explanation or the contemporary scientific methodology and the phenomenon, but nobody says that we can't change the contemporary scientific methodology. And in fact, so in this case, we can even see that mathematics can help this. So let's assume that, so previously P was just this, a space of configurations. Let's assume we have actually a proper theory TP, where we actually, we get trajectories, states, basically how physical states evolve in time, and some time parameter I. And then you can show the following theorem. So basically, if a theory of consciousness is supposed to be empirically intersubjectively well-defined, well, it needs to comprise at least the following quantities. Well, it needs to have some dynamical variables, state of consciousness, physical state. That's clear. It needs to have what we can call kinematically possible trajectories. So these are just, how these states, which we had up here, evolve in time. It needs to have some laws. We don't care which mathematics are being used to actually formulate the laws. What matters is that they pick then from all possible trajectories that you could write down. They actually pick a few that, according to the theory, are actually possible in reality. So we can call these solutions, or D for dynamically possible trajectories. And these three features are really something you always have when you formulate a model of consciousness, even though you might not write it down explicitly. You typically have some sort of principles that allow you to somehow tell you how the states of consciousness and the physical states co-evolve, at least in a certain sense. You have some laws which tell you which of these evolutions are. So put differently, you always can write down these, you have a notion of states, of physical states and consciousness states. You can always write down these variations, and you can then use the laws of the theory to pick out which one of these are actually realizable. But something that actually follows from that theorem is something more, namely, there needs to be a particular symmetry. So E is the space of states of consciousness, out E are the automorphisms of that space, and the theory needs to carry an out E symmetry. And here's just what this means. So this means you have a group action that takes a group element and a kinematically possible trajectory. And what it gives you is another kinematically possible trajectory. And the form of this is like this. So you have a group element, here's the trajectory, and then this group element just transforms the state of consciousness according to, the automorphism which G represents. And the crucial bit is actually, and then here you can do something. So that's the requirement still of something being a symmetry. But the crucial point is that, so this is really just, maybe let me emphasize this is just an exposition of what it means to be a symmetry. And the crucial point is that this out E symmetry can do something with a physical part of the trajectories of the model of consciousness. And that follows again from the requirement of being intersubjectively well-defined. So what does this mean? How we can understand this? Well, automorphisms of the space of states of consciousness, well, what they do, if you set everything up correctly, they map states of consciousness to other states which are in the very same equivalence class, so that they cannot be distinguished in terms of what I've used in this talk to present this idea. They cannot be distinguished by the subject under consideration. So what this means formally is that this E tilde, which we've had in the beginning of the second part of the talk, is actually just the space E modulo the automorphism group. So that's again the quotient here. But above, we found that the contemporary scientific theories of consciousness are limited to this sort of set. And so what that means in terms of theorem 2 is that the contemporary scientific study of consciousness, it does consider an automorphism, or at least it has to if it does things properly. It has to consider, or it does consider, an automorphism, group symmetry, on the model it constructs, but it considers a particularly simple symmetry and is characterized by the second part of the action being trivial. So that's very much like, when we did special relativity or even Newtonian mechanics, we were working with a concept of space that we thought was nice, but that we later learned when general relativity came around that was actually a very simple special case of the general concept of space. General concept being pseudo-Riemannian manifold, specific concept being Minkowski space or even Euclidean space. And that's a similar thing here. So what I'm saying is two things. So first of all, we don't actually take into account that there's this limitation when it comes to non-collatable aspects. We need to, but even if we do this, then if we take it into account, what we'll work with, as long as we use the standard methodology, is a very simplified symmetry, and not the general class of symmetry. So in fact, like these, a little bit intuitively speaking, we work with a subset of measure zero of the actions that are actually possible. So with something very specific. And that is a fully unnecessary restrictions. The mathematics allow for many more symmetries than the ones which are trivial, the ones which we actually consider. And the crucial point is that the non-trivial phi g, what it does, it transforms the physical states along with the states of consciousness. And therefore, it allows to address individual states of consciousness while still ensuring that the theory, which we consider intersubjectively well defined. So something I can't say very well in this sort of approach I've taken here to actually show you these results, which is a little bit different from the actual paper. I hope they are more intuitive and more accessible. But something I can't argue, but I'll just tell you here, is that you can actually make sense of this as follows. So what we have to do usually is we have to implement intersubjectivity. And then the standard methodology corresponds to first implementing intersubjectivity and then studying or hypothesizing about how states of consciousness and physical states relate. And what this this general possibility here that the mathematics just allows us to do is to exchange that order. So we can first say something about the connection between physical states and states of consciousness and subsequently implement intersubjectivity. Okay. Yeah, so that's been quite some tour de force, I think, at least at the end concerning mathematics. And I'd just like to conclude maybe in a minute. So even if the very last bit was a bit too technical, it's easy to understand, but it may take some time, much more than I've just given to it. I hope I can bring it all together in the conclusion. So the main point I wanted to get across is what makes the scientific study of consciousness difficult. So the scientific study of consciousness, I should emphasize scientific, is consciousness unique epistemic context. And just to repeat again, so epistemic concept means roughly, it refers roughly to the possibility of gathering information about states of consciousness. There's epistemic constraints on the physical side, but they are usually of a practical nature. And in consciousness, we have many more. They are of different kinds. And these things sort of determine the possibilities we have in a scientific concept. And while we have a lot of thoughts about metaphysical ideas, how consciousness could relate to the physical, we have idealist theories in the case of IIT. We have at least metaphysically idealist. We have physicalist theories, and there's many different proposals of which are of a functional or even of an identity type thought. However, I would think that at least within the science, the epistemic context of consciousness has largely been ignored. And that was really the focus of this talk, to devote some time of studying these and show you that there are certain problems that loom in the dark, which we're kind of ignoring. So in the first part of the talk, I've shown that there's a widespread assumption about the epistemic content of reports, namely that reports can be interpreted independently of the theory of consideration. And that assumption generates a thorough problem in the usual scheme of testing theories. So as indicated, if you do an experiment, you confirm the theory,
if you haven't thought about how the report relates to the theory, well, the formalism shows you that there would in fact be, there is another physical system that you might have well as have tested, at least in principle, and that would have given you a falsification. So in a certain sense, the confirmation is, you can't build on the confirmation. So that was the one thing. And I'd just like to emphasize that this is an epistemic problem, right? It concerns, so we pretend that our knowledge about the report is sufficient to infer the state of consciousness. And it may be, but there's a problem if we don't relate that back to the theory. And in the second part of this talk, I have sketched an axiomatization and subsequent formalization of some of consciousness' more problematic epistemic features. So the features being, the list ahead, intrinsicality, privateness, until unavailability to cognitive success, and axiomatization being the notion of non-collateability. So I worked that out in much more thoroughly in this paper than I could sketch in this talk. And I have used this to show that there's actually a boundary we will run into, or we have already run into, depending on what a study does, when it comes to sort of studying consciousness. And I have outlined how mathematical approaches can help to overcome this limitation. And the mathematical approaches in this case would just be a slight modification of the methodology we already use. Okay, so that's it from my side. Many thanks for the attention. I hope I was able to clarify some of the ideas I had in these papers. You can find the sources here again. Yeah, and I'm happy to have questions or criticisms or objections.